So, good. Good morning, everyone. I'm Giacomo Bergami, and I'm going to teach you the first half of the module. The second half of the module is going to be dealt by Chris Holder, and in addition to that, then he will be also the one responsible for setting up the marking scheme for the coursework. So there's going to be no exam unless you are doing a recit. And also that is going to be prepared by Chris Holder, by the way. And in here, given that the module has been restrained in the time of teaching, so we cannot do everything in one shot. So we provide most of the introductory material on Canvas on how to set up and to make a Unity game. On the other hand, due to cause majeure, I'm going to do the AI part first, while the more game mechanic related, like to physics, is going to be taught by Chris Holder. But notwithstanding the former, still you're going to have a lot of PDFs and zip files for projects, where you're going to have like introductory material on the basics of this. And also my other suggestion is that all the things that I'm going to teach is going to be available into a separate project, which is going to be like a solution using Visual Studio, but you could also import that using a compilation of a DLL, either this or by directly importing the scripts within the Unity game engine as a separate CIS file. So those are the possibilities. And in addition to that, you're also having like my GitHub account. Not this one. So if you're going to looking for, I'm saying for the ones that cannot see that sharply, github.com/JACKBERGUS/NCL_CSC3232, then if you're accessing that, basically you're having the same material, but you're also having on Canvas, but that is actually on GitHub. Why? Because there are also other implementations about material that was completely removed to the time constraints and possibility of implementing some of these algorithms in C++. So, but notwithstanding the former, the only thing that we're going to focus due to time constraints is going to be teaching on C#. And given this, then I would start straight away with this. So I'm using not final state machines or blah blah blah, but the actual name that is actually used in literature, which are Harel Statecharts. You could also have like UML diagrams that are also called Statecharts. So the thing that I'm teaching is going to be related to this, because that is actually the more and comprehensive kind of setup that you could possibly have. So at the end of the day, the objectives of today and this hour, as much as possible, we're going to recognize the need of an untrained based AI and why those are suitable. And I'm going to teach you how those can be directly connected within Unity. So to connect the action associated with an agent with specific reactions. And I'm also teaching how you could determine which are the different kinds of states and how events can be triggered just by providing a physics or probing-based kind of environment. And I'm also giving you suggestions on how this kind of simplistic state machines could be mixed, stochastic, but adding a random number generator. But that will be discussed in more detail eventually during these slides. So this is actually a comic coming from a web comic that is not available anymore, Abstruse Goose. But anyway, that was somehow mocking training-based AI and showing that there are some limitations in the things that they could do. Also, in very critical scenarios, you're never going to use training-based AI for the simplistic fact that you cannot possibly train over all the possible circumstances. While if you're doing a by case analysis, then you could fully cover that using untraining-based technologies. So that's why critical use case scenarios are non-training based, thus motivating why the need of one kind of those, allegedly, for example, Statechart, but not necessarily those, are successful approaches. Also, the other problem is that at the current state, if you're just having a training-based system, it's hard to debug and to fix the problem, for example, in real time. So because you're having the outcome, but not the explanation that is giving you the consequence of the actions, while there are other systems that are actually giving you this kind of information, and the outcome of the reasoning is still represented as a graph. So I'm not going to discuss in very much detail because it's actually an advanced research topic, but at the end of the road, the thing which we're building is basically a graph. Still, they're also guaranteeing 100% success, but then the limitation is not related to the technology itself, it's related to the one using the technology. So in this scenario, because you could also provide a very thorough system, and if you're missing one case, it's just the person that is missing one case. It's not the technology, it's not versatile, it's the person using that. And one use case scenario was actually The Sims, because even there, the first version, they tried to make all the possible interactions without a training-based AI, but just connecting the conditions of the post conditions, similarly to another game called FEAR, but is actually not learning based, but is actually rule based. And the only problem with that is that the systems still are not very good with randomicity, so you are somehow in need in a video game to add variety, so that's why you're having this kind of non-deterministic kind of behavior, but that could also be simulated by using probability. Then I'm just contextualizing a bit. If you're having already knowledge about Unity, which is the most straightforward kind of state machines that you already might have encountered. One kind is actually the one triggering animations and events, as you can see in there. So usually, let's focus on an animation, and there the focus is to make a character follow specific animations which are dependent on the commands that you are providing. And so you could have locomotion, jump, idle, and roll back. And definitely you want to run a specific animation if it is actually in a given state. And you're also having some constraints, like for example, you cannot jump while couching, as you need to stand first. And that is not only embedded by the logic of what should be done, but also within the state machine. So the thing that you are reflecting is which is the order of action in a suitable way by connecting that with directed edges. You could also remember that you cannot run while jumping, as you need to land first. So you are providing a set of states where the machine or the agent resides, and depending on that, then you could say which is the action that could be performed. So in here, you also have a juxtaposition between the state and the action. Usually a state is more generic than a specific action. It could also be the state the agent is in. So to be like more flexible. So in here, basically, the thing that you're saying is all the outgoing edges are representing the possibility of performing one action, and the state itself in here represents the action which is undergoing. But that could also be further generalized by just representing the state of being like chasing someone, or for example, if you're having like more complex situations which are beyond the purpose of a single animation, you can also have like patrolling, chasing, or retreating depending on the conditions. So it's also depending on the internal state, which are the variable describing the agent. And so that's why you could also have states associated with variables which are persisting like decision in time. For example, if you need to update the ammunitions or whether you are able to respond to an attack. Then let's see another thing in here. So what is actually the rationale between any kind of AI? So there are differences between training-based, supervised, all this kind of stuff. But ultimately, they all boil down to this kind of mechanism, which is the one usually adopted for reinforcement learning, but this kind of perception is also used in verified AI, is also used in other domains, not necessarily reinforcement learning. So in all the possible situations, the non-player character or any kind of agentic AI, it's always trying to perceive the environment because it's actually from that perception that you're driving your own decision of what needs to be done. So the thing that you're doing is that after the perception or probing the environment, you are making a decision given the internal information, could be like a training-based logic or hard-coded one, and depending on that, that leads to an action which is performed through actuators. And you see, you could also apply that to an industrial setup where you're having sensors and actuators, so it's not necessarily related to video games. And those actions are usually providing not necessarily an action within myself. It could also be like that if the sensor is just a collision sensor and then I'm reducing my own health. So you could also have actuators that are reflexive and inwards, and most of the time in a video game you're interested not only on self-reflective actions but also actions changing the game logic. So basically that's why there are actions towards the environment, which the environment in here is seen as a holistic agent comprising of different non-player characters but also the human player within the video game. So the environment is just a generic term for embracing everything. And that is to be like the idea of whenever you are designing a class, usually describing a non-player character. So you need to think, what are the perceptions? So a collision event, or that could be, for example, a time update. It depends on what you want to do. And depending on that, you are providing actions. So, for example, some examples are given below. So, for example, if I'm hitting the opponent, we might need to change the behavior, so to chasing the enemy. If we identify an obstacle, we might decide to perform a specific contextual action, so jumping across rather than running or walking. So you see, that is changing the inner logic of the agent, and it's updating basically the mental state of the agent. And those are just possibilities that could be done. Let me see if before I'm asking questions. Okay, then just to contextualize, why are we focusing on 5-state machines? Because those are thoroughly used in our everyday lives, not only in video games. But even if you're using like a compiler, and if you're using a programming language, then implicitly you're also using a 5-state machine. Something quite specific though, which is called like something for recognizing a language, usually. You're having like a combination of graphs, so one for the rules and another one for determining the input chain. But still, even whenever you are writing something along the lines of a program, then you're converting that to an abstract syntax tree, which is actually going to yield byte code or just the machine code. And even that is an abstraction of receiving a set of actions. It's perceiving a set of changes of the environment. In that context, those are the tokens on which you are tokenizing your program. And then depending on that, you're making the decision of which is the bytecode instruction that is going to be yielded. So even in this scenario, the 5-state machine acts as a translation between the input that the program is receiving from the manual input to the bytecode or to the binary program that is going to be generated somehow. And but those are just an abstraction, so just a string or a token that I'm seeing, that becomes the thing that I'm perceiving for the environment. But that could also be related to a timeout. So even a timeout could be an action. I'm waiting for a given amount of seconds, and if nothing happens, then I need to take a decision, for example. So even those kind of elements could also be framed within a 5-state machine as an action that is actually very used in embedded environments. Whenever you want to do something, wait up until a given amount of time, and then after that you are taking a decision. So that could also be easily modeled if you're binding a state machine with a set of states with internal variables and with a counter. And then you could also mimic this kind of timeouts. Yeah. So, as I was mentioning, then software engineering, basically, if you are. Another thing is, another application is that you're already having some tools that are available that are translating a finite state machines into code directly. And that is actually just a subset of this kind of tools is the thing that I'm suggesting you to use for the coursework, because you could just draw this finite state machine rather than hard coding that step by step. And as a consequence of that, you will be generating like some C# code. I'm going to provide the link eventually in the slides. And then, as I was mentioning before, that is also another use case scenario is on embedded systems. And both are also industry related. So this kind of knowledge is cross-compatible not only with video games, but even in the real job market somehow. And even in an embedded system, then even if you want to create a robot or a control system, or even when you're defining a communication protocol or any protocol across communicating agents, then that is actually somehow formally as a state machine, which is actually checking the compliance about something. And the important part is actually they are robust in terms of, you know, if something goes bad, which was the chain of actions making something bad. So the debugging is actually more explicit. Then I'm going to stop and ask you if you have questions, and then I will continue for sure. So now, given that we are in a video games environment, I'm just providing you like more holistic view of Statechart. So I'm providing also the GitHub link to the repo that I'm suggesting you of using. So usually there are different setups. So if you are clicking on that, so it should also work now. So let me still go there. Statesman. So this is actually the project that I'm suggesting. So in there, you could just download the binary, so you don't have to compile everything by yourself. If you're going to the Statesmith project and you're going to the releases, eventually down below, you should see some set of binaries within the assets. And then you should have like zip folders, which are also convenient because they do not require any kind of setup. So you just need to download the Windows binary, unzip it, and that will do. And that will set up somehow some local user configuration, so you don't have to install anything at all. And then I'm going to show you basically what you can do with this kind of tool. Usually the way which is actually suggested is to use online tools like Draw.io, for actually the GUI for defining the state machine, while the local binary will generate the source code after the diagram that you are generating online. But going back to the slides, let me give you another example. So can everyone see that clearly, or do I need to zoom the image in? Okay. Anyway, no answer. So nevertheless, I'm going to provide some kind of verbal explanations. So this is actually quite an example of a complicated state machine, which is also nested. Let's focus on that later on, shall we? Just to provide like a context on how something well-designed is structured, so different from usual video games which are not providing the initial state, which is actually a big no-no. In there, you're also having the initial state, which is the circle atop, the one linking directly to the small state. So you see in here, the state is not necessarily connected, as in the previous example, to an action, rather than to the state of the agent. So the agent now, like Mario Bros, so just Mario, from Mario Bros game, is actually in a small state. Given that in a small state, then there are some actions that I could perform depending on my current state. So for example, I could be hit, and then for example, I'm having a method which is defeat Mario, for example. And then I'm checking whether I'm dying or not. And then if I'm not dying, maybe there's something to do with the mushroom that I ate before. And then on that circumstance, if I have a mushroom, then I could go back to the small state, so nothing happens. And anyhow, I could also do something about checking, for example, any kind of animation. And that is done in entry point, small Mario. So whenever I'm entering the state, I could perform an action. In this case, I'm invoking a method called small Mario. From there, I could either fire a flower, or I could take a mushroom, so I'm colliding with a mushroom, or I'm having like a feather. And then you see something quite interesting in there, is that you could transit, so any of these actions are transiting you towards a large state. But there could be, so large state is somehow just defining of Mario being big, but then there are some specificities depending on where it's residing. So you see, I could have either a feather or a fire flower, and then depending on that, I might have two different entries, but they're going to lead me to different cape or fire actions. If none of those are specified, so that is actually the default one, which is just the super state. Okay, the thing that is actually going to happen is whenever I'm transiting to another state, which is not a hierarchical state, then the only thing that I'm doing is basically just performing the enter action, if any. Otherwise, I'm not doing anything and I'm just waiting for an action to occur. Otherwise, if I'm having like a hierarchical or a nested state, then I'm activating the underneath entry point, and then from that I'm transiting to the forthcoming state. And then depending on that, you could also do like a set of actions, and you could see that that is somehow concurrent to the action hit. So what is actually the interpretation of it? Because you see, from the large, I could go back to small, but there are some specificities. So, for example, if I'm having the it transaction, for example, within cape, then if I'm in a cape state and I'm hit, then there is actually a transaction going back to super, so I'm not going back to a small state. On the other hand, if I'm currently are in a state which doesn't have an hit outgoing edge, then that requires to go back to the small state. So in this way, basically, you are providing a more convenient representation which is equivalent to an unnested state machine, because you could also represent this equivalently into an unnested state machine. But the benefit of using that nested representation is the compactness, and is to avoiding considering like multiple edges going out of a specific state and providing just a compact representation. And in there, the same thing will happen. So depending on the actions, I could also transit within the large state, but if I'm hit and I'm in either a fire or a super state, then I'm going back to the small configuration. And another thing is actually, so a state is just describing the configuration the agent is in, not necessarily the actions, but the state dictates the actions that are possible anyhow. So given that I'm in a specific state, that I could only perform a specific set of actions, but not everything. So it's just restricting my search. Before I continue and provide further examples about that, do you have any questions concerning this? Yes? Yeah, you could also have arbitrary nesting. So that could also be like in arbitrary depth. So you could also go, again, another time inside, inside, inside. So there is no upper limit or no upper bound or no downwards limit. So another example which is going to be more easier for you, I think, if you're actually checking the Harel's paper, so you're checking like Statecharts, and you're checking for Harel, you would find a paper where it was basically discussing how to model like a smart, not a smartwatch, just a electrical watch with different states. So in there, you could also have another internal state, could be another internal state, so it could be arbitrary nested, yes. Does that answer your question? Okay, yes.
How do states usually share code? Because I'm thinking like the super and the cape, they'd have the same sort of run state, wouldn't they? So like they're not really nested, they're sort of like...
No, so you're describing like that because you're not separating the responsibilities. So in software engineering, there is something called the principle of responsibility. You're thinking more about the entry point. So there should be a run method, which is run at each delta update. So that is actually what you're referring to. But if you're injecting everything within the run, then you are not modeling your solution in a reusable way. So the thing is, there is one common entry point, but then, actually, in order to answer that question, I'm actually going to discuss that directly. Is it this one? Yes. So this somehow, let's just focus on the right side, which is actually the thing that you asked, okay? So, and basically you asked the below part. So how does that work? Whenever you're initializing an agent, you're always having like a start method, or like initialization even in Unity, and that will set up basically the state machine, because you're starting for a specific state. There could be like a specific configuration either loaded from a file, or it could also have like multiple non-player characters that are differentiating from the configuration. So that is done at start. Then you're having your delta update within the update method, and within there, basically you are checking for any kind of what is called, for any kind of non-timeout event, for any kind of timeout event, for example. So the thing that would happen by well structuring your state machine is that at initialization is where you're initializing the state machine. Then you're going to have, for example, collisions events, and those are directly interacting with the state machine. Because in there, then each update event, each on-collision event will trigger one transition. So for the state machine itself, which is encapsulated within the non-player character class, you will say, okay, now I want to perform this transition. For example, I'm having a collision, and your collision is against the mushroom, that will trigger a mushroom transition. Otherwise, I'm colliding, for example, against an enemy, and then I'm having like a hit kind of collision. And then, for example, if you are already confident with Unity, each game object could have a tag. Depending on the tag, on collision, I'm checking the type of the tag, and depending on that, I'm defining which is actually going to be the transition. So the state machine at collision time is going just to feed the event corresponding to the agent that I'm colliding with. If I'm having other non-collision-based events, those will be, for example, on a delta update, I'm proving the environment. For example, I need to look for enemies. I'm moving from a patrolling state to an attack state. That could also be related to like what is called to raycasting. I'm doing a raycast or like a sphere cast, and I'm checking whether there is an enemy within the radius. Depending on that, I'm changing the state. And that is actually triggered by an event. And the event is basically within the update, you are checking for raycasting, for example. Is there an enemy here? Yes, no. If it's yes, then I'm triggering a transition, otherwise not. So the thing is then the update and the initialization and the on-collision, in order to have like a very good code separation, should be the only parts when you're doing the checking about the conditions or the type of the collision, and depending on that, you're doing the event transition. Well, on the other hand, the class for the state machine will be the one handling the logic for the transition. So the only thing that you need to do is just to specify like the event, and potentially that is actually the only caveat. The only caveat is that not in this simplistic representation within this library, but you could also have a message associated or a value associated with the event. for example. You could also differentiate between different kind of collisions depending on the force, like either light or strong, or depending on that. So a simplistic way is to discretize that into distinct events. Or if you want to be like real valued, then the thing that you could also do, like in proper state charts, is to associate a message with the event. That will become the payload of the message, and then the receiving state will update its internal state depending on the event. Another thing, just to conclude my discussion, is that whenever you're entering and exiting a state, you could also have a method. Those are usually local to just the state that you're in, because you want to do a specific action which is specific to the state. So if the action is moving right, then the method is just while the opposite, so just move right, okay? And if I'm going to move left, I'm moving left. If I'm a Roomba kind of use case example. And in here, the count is just counting the amount of steps that I'm doing before colliding against the wall in this example. So the answer is the logic, which is actually in common across all the method, should be within either the update or on the collision or on trigger kind of states. While on the other hand, this class allows you and the structure to have like a better separation of the logic, so you are not intermingling too much with the logic itself. So if you're confident with design patterns, it's more like having a model view controller on which the state machine acts as the model. Then you're having the view, which is just your game engine, which is visualizing, and that is actually opaque to you. It's just happening somehow. And then the class of the non-player character acts as the controller part, which is just checking about the conditions and updating the model accordingly. Okay, any other question? So, as I was mentioning before, the thing is that this helps you to code also according to one principle called the responsibility principle, which means that, which is actually something that not all the students are doing automatically, which is the class containing all the variables should be the one performing the event or the action. Sometimes it might happen that you are checking the collision of a non-player character against, for example, a target. And then the action that the enemy should perform is done on the target, while it should be like on the other way around. So if the action uses properties of the non-player character, then all the operations should be within the non-player character and not in a target which is actually oblivious. And by doing that, somehow you're also ensuring to have some kind of code separation. Then it also is related to the question that your colleague was asking. Then I could also have the same action or the same response which is shared across different NPC agents, but then it's actually a matter of parameterizing the code. So I'm just having one single code or one single method which is parameterized depending on the non-player character. And then depending on the situation, I might want have a slight modification on the action itself. So it's actually better to have something like code reuse rather than in this way, rather than reinventing the wheel several times and still moving the action that should be associated to the on collision just on the obstacle is actually not a good practice, because then it's responsibility of the object colliding against that to change its action according to the information which is withheld inside it. Any other question? Okay. So then there is actually somehow a difference between collisions and triggers, which are mainly defined in the way you're setting up your collider with the variables, but you're going to see that with Chris. On the other hand, my suggestion is actually that for the time being, if you're just focusing with the collision, is going to be fine. Then just for having, usually then Chris will be the one revising the coursework marks this year. But if you're going to have different marks for triggers or collision, then it's going to be helpful. Otherwise, if that is not required, just focusing on one of the two will be fine. So in this scenario, as I was discussing, you're having something which is collision driven, And then depending on the environment, I'm just either moving left or right. So in this case, it's actually a dumb kind of robot, which is always moving in a line. And then when it's actually colliding against the surface, it's actually going back. So, and going backwards like that. So it's actually more acting like a game of Pong. And the only thing is, given that it's actually just moving in a line, not even in 2D, the only action that you're having is just the collision, and then given that, I'm moving backwards. Of course, if you're having like a more complicated scenario where you're having like navigation within the setup, then the thing might drastically change, but that is actually just to give you a somehow generical view. And you could see that all events could be when describing your scenario. So my suggestion is to create like a storyboard describing your game, and whenever you're defining a non-player character, you are highlighting all the verbs. So when you're detecting an enemy, you are trying to, when you're going into a mode, then you're going to a state, but then until the enemy goes away, you see it's just providing a condition, and also the conditions are to be modeled as events. So all the verbs and the conditions are events, while states are anything describing a change of strategy. So you could also model your system as such. This is actually also restating what I mentioned before. So you're going to also have a start method if you're using like your Unity. Within that, you're initializing your state machine and the way you're controlling the player, as well as invoking the start method. So, for example, if you're using this library, so if you're using like Statesmith, you're going to generate associated with a state machine having a start method. So within the start, we're invoking the start method of the state machine. It's actually better to do it this way, so you're not, so you're having somehow better object encapsulation, and you're providing a separation between the controller, which is going to be like the Unity script governing the NPC, and just the state machine being the model that you are looking for. Then, as I was mentioning before, whenever you're having a collision or a trigger, that is actually going to potentially trigger an action through an event. That will also be conditional based, as I was mentioning before. And in order to do that, you're having a specific method, which the library is providing you, which is dispatch event. So dispatch event is basically doing the following. Independently from the state where the state machine is trying to move and follow an edge having the label associated with the enum that you're considering, basically. And under a circumstance there is no state having this outgoing transaction, then you're going to be blocked in there. That is actually the rationale. But that is actually not sufficient, because as I was mentioning, some other scenarios are non-collision based, but are event based. So the other thing, as I was mentioning before, is to use the update methods. Within that, you are checking for environment conditions, so you are using the sensors somehow of the agent for probing the environment. And those are also the so-called non-physical events. And then the other thing is, okay, all good, but everything that you mentioned now to me is completely deterministic. How do I add stochasticity or probability in that? So the thing is, usually you need to provide probabilistical distribution across all the outgoing edges that you're having within the model. If you're taking like model MDP, which are Markov decision processes, is slightly different, but the idea is similar. So the thing is, for each event that could be an outgoing edge from the current state, you are also defining some probabilities, P1, P2, and P3, of the likelihood of those happening. And then you need also to guarantee, given that is actually a distribution over the outgoing edges, to have that they are summing up to 1, potentially. But the thing is, how could I then determine which is going to be the event which is actually happening? So let's suppose that you're having a fully probabilistical kind of event, which is within the update method, for example. Then the thing that I could do is to use a random number generator by using, for example, next double or something more sophisticated, and then check for this condition down below. So what does this mean really? So your P here is going to be the double that you're randomly generating, and P1, P2, P3 is the sum of all the probabilities which is actually associated with the event that you are considering. And then you're checking, in order to generate the event I, whether P is between the summation from P1 up until Pi and Pi minus 1, and the summation between P1 up until Pi divided by the total sum of the probabilities. That is just to ensure normalization if under the circumstance that your sum doesn't add up to 1. If that doesn't add up, does actually add up to 1, then it's actually not required. Okay, that is just for braces and bells programming. So, and then basically you're checking whether your value is within each of these intervals. If that is a yes, then basically the thing that you're doing is generating the EI event. So you'd see that will also be done within that day, for example, and that will also generate for you stochastic events, which are completely associated with random number generator. So you're not forced by just probing the environment or anything of the like. Any questions about this bit? And in here, I'm also giving you an example on how to avoid some kind of specific problems. So there could be situations where the agent is actually considering a lot of actions at the same time without actually any further consideration. So for example, let's suppose that this is actually something quite simplistic and quite unrealistic, but anyway, just to give you something to think about. Let's suppose that you're colliding against an obstacle, and this obstacle is moving, and then this obstacle is moving, and then you're recolliding again, because the object is moving too, so you might end up with moving left and right continuously, and basically not progressing any on one further. So the point is somehow to add a delay between the decision of the collision and the thing that you are looking for. So what is actually the best use case scenario? You're going to also have a problem like a solution of this within the code base that I provided you. So timer.delta time is somehow a trigger that I'm doing in order to have the current delta time within the class by creating like an additional class. So I'm able to get the time even within the state machine, despite it not being directly connected to the delta time as in Unity. So the thing that I'm doing is basically each time that I'm invoked, the thing that is actually going to happen is whenever entering the state, or whenever I'm doing something, it could also be like an empty action doing nothing at all, for example. I'm constantly incrementing the counter, for example. And then the thing that I could also check is how many steps were elapsed since the previous collision. So I'm basically checking how much time it passed. And if the time is actually sufficient, then I'm performing the transition with a condition provided in square brackets. Otherwise, I'm staying there. So how could I model that? Because if you're using the Statesmith kind of implementation, you're not having timed transactions as in Harel Statecharts or in UML Statecharts. So the only thing that you could do is to use actually a delta time, incrementally counting the seconds inside of that, and then using the timeout as a condition that you're checking on the update method, basically of your non-player character. And by doing this, you are basically avoiding the possibility of moving left and right continuously without actually checking a state of progression. So this is actually called hysteresis. So basically the thing that you're doing is also adding a padding zone, because if the interval is also similar, you can also still ping pong between those two. So the thing that you're doing is adding like a slight time interval of difference in order to avoid this kind of repeated kind of actions. Is there any other slide? Yeah. So this is actually something that might be useful to you. So the thing that is actually going to be provided by the tool is also a demo, which is actually showing you what would happen whenever events are occurring. So if you are setting up the configuration in a good way, it's actually going to generate for you an HTML file, which is going to allow you to simulate the state machine. So the thing that you could do is to show where you're starting from. So for example, in this kind of example, let's suppose that you are modeling another character, but he's actually trying to chase a human player. So in there, you're not having like the conditions as in Unity, but you could also say, okay, now this event is triggered, and basically you're seeing where you're ending up with. So that's why I'm saying that state machines are somehow debuggable, as much as, let's suppose that your game is not working as you are expecting, rather than running the game several times and being blocked, the best that you could do is basically simulate the events within your state machine, check where you're ending up, and then depending on that, rechanging again the state machine. So the suggestion is, if you're using this kind of modeling for implementing your own solution, then you're not forced to recode the state machine when you're changing the logic. The idea of using this kind of tools is just to change the graphical representation so that is automatically generating the code for you and potentially also updating the variables, because the syntax somehow might allow you to do that, and also using the HTML interface to check if you're actually ending up in a place where you're expecting. So also differently from the other usual implementations, the other thing that I'm doing is also adding no operations, because there could also be the possibility of continuing to run away, or for example, continue to move to base independently from the possibility of any kind of actions above to actually occurring. So you want the game to basically continue to move, even though none of these events are happening. So no operation is basically saying, I'm continuing to do the action that I'm supposed to do. And this will also help you to better model your state machine. So you're not just saying, okay, in these states, and then in the next update, okay, I'm not doing anything. You could force any kind of operation, because usually the enter method that we were discussing beforehand is just whenever you're entering the state for the first time, but not when you're actively updating the state. So you will also think that if you are having a counter, for example, also no operation will incrementally increment the counter to. Yeah, there's actually a separation between update and the dispatch event, as I was suggesting before. And exactly, so those basically the no operation, given that you are going out and re-entering, they are somehow forcing the re-entrance to the statesmith. If you're taking UML, semantic is quite different, because actually you're never going out of a state if you're having like a hook, like in this example, so you're never going to invoke enter. So the semantic is quite different. But when I was using this library back then, they had a different semantic. So each time when I was using that, you were traversing an edge, basically you were re-entering the state and exiting that all the time. And this should be the last slide. Yeah. So last but not least, this is actually another example of a state machine, which is basically another use case scenario. And even in there, you could say that I'm also adding, in this case example, also probabilistical events. So you could see I could have E1, E2, E3, and E4 as randomly generated events with probability of 50%. Why? Because actually in this case, I could also add some kind of variety to the game itself. So that could be like quite erratic, but the thing that I'm doing is if I'm patrolling, I'm starting off being idle, sometimes I'm wandering, and then I'm doing some kind of patrol, and adding this kind of stochasticity allows you to have like a more smooth kind of interactions, but that is actually not strictly required. And then the exercise was somehow mentioned beforehand by me, so basically in that way you could connect that. So for you, the exercise is actually more, how could I implement that for real? Yeah. So the other thing that is actually you need to care about is, well, I'm using a tool, and I'm trying to use like a hierarchical state machine, but that is not providing any kind of hierarchical notion. I'm seeing everything flatten out. Is that how it's supposed to be? Well, the thing is, yes, because it is actually just for convenience, even though you're going to have like a state explosion, because you need to consider all the possible combinations between outside and internal state and do all the possible combinations of enter and exit. Nevertheless, for economy of code, it's actually more convenient because you're just having one code for a state machine. Given the hierarchical state machine, you're flattening that out to be unnested. There are some trickery that are basically connecting each edge from being shot from patrolling to each internal state, and that being shot is not necessarily always connecting to take cover, for example, and from all the states, retreat, take cover, shoot player, you're going to always to have like one state each for each other wander, patrol, and player idle, for example, because that edge is within the state itself. So the tool for you will flatten out this into a more verbose way, and notwithstanding the fact that you're going to have at the end a flattened out state machine, at least me, as far as I'm concerned, your implementation is hierarchical because the tool that you're using is basically allowing you to have some kind of abstraction that allows you to not care about drawing all the possible edges, but have like a bird's eye view of the system, while it's actually the tool itself which is flattening that out. So, notwithstanding the former, your conception is hierarchical independently from what the tool is doing for its own efficiency. So, and that is also because those are completely equivalent, and there are basically theorems proving that. So that is actually what I could say in less than 1 hour. We have 3 minutes left, so do you have any questions concerning what I was teaching you today? Then, if not, then we're going to see each other during the practical sessions, and thank you.